Look up at the night sky on a clear evening far away from the glare of city lights. You will see an ocean of stars, countless pinpricks of light scattered across the blackness. You might see the faint glowing band of our own Milky Way galaxy, a river of stars containing our Sun. If you are lucky, you might even spot the faint fuzzy patch of the Andromeda galaxy, our nearest large galactic neighbour so far away that its light has travelled for over 2 million years to reach your eyes. This is the universe as humanity has always known it. It is vast, beautiful and overwhelming. We have spent centuries building powerful telescopes to peer deeper into this darkness, discovering billions of other galaxies, nebulae and cosmic structures. It seems infinite. But here is a fact that is both humbling and terrifying. Everything you see, everything we have ever seen is just a tiny fraction of what is truly out there. All the stars, all the galaxies, all the planets, the gas, the dust and even us, our bodies, our planet. All of this normal matter, which scientists call baryonic matter, makes up only 5% of the total universe. Think about that. 95% of reality is completely hidden from us. It is a hidden reality that governs the cosmos, and we are only just beginning to understand that it exists at all. This missing 95% is not just empty space. It is composed of two distinct, mysterious components that control the entire structure and destiny of our universe. They are the true actors in the shadow, and they dominate the cosmic stage. The first of these hidden actors is called dark matter. This component makes up about 27% of the universe, meaning it is more than 5 times more abundant than all the visible matter combined. We call it dark, not because it is black, but because it is completely invisible. It does not interact with light in any way. It does not shine, it does not reflect, and it does not block light. It is utterly transparent. We only know it exists because of its gravity. We first discovered the need for dark matter by watching how galaxies spin. Stars on the outer edges of spiral galaxies orbit the center much faster than they should. Based on the gravity from the visible matter, the stars and gas, we can see these outer stars should be flung off into deep space like a child flying off a merry-go-round that's spinning too fast. But they are not. They are held firmly in their orbits. The only way this is possible is if the galaxy is surrounded by a massive invisible halo of extra stuff providing the extra gravitational pull needed to hold everything together. This is the job of dark matter. It is the invisible scaffolding of the cosmos. It formed the large-scale structure of the universe, acting as the framework upon which visible matter could cluster. The galaxies we see are like the glittering lights strung up on a massive invisible structure that we can never see directly. Dark matter is the glue, the cosmic cement holding galaxies and clusters of galaxies together. Without it, galaxies as we know them would never have formed and we would not be here. The second and even more mysterious hidden actor is called dark energy. This component is the absolute dominant force in the universe, making up the remaining 68% of everything. If dark matter is the glue that pulls things together, dark energy is the exact opposite. It is a mysterious pressure that pushes things apart. For most of the 20th century, astronomers debated the future of the universe. We knew the universe was expanding a result of the Big Bang. The big question was whether the gravity of all the matter, both visible and dark, would eventually be strong enough to slow this expansion down, stop it, and perhaps even pull everything back together in a big crunch. Then in the late 90s, astronomers made one of the most shocking discoveries in the history of science. By observing distant exploding stars, they found that the expansion of the universe is not slowing down at all. It is speeding up. This discovery was revolutionary. Something must be overpowering the pull of gravity on the largest cosmic scales. This something is dark energy. It is an invisible force, a sort of anti-gravity that seems to be a fundamental property of empty space itself. As the universe expands, more empty space is created. And as more space is created, more dark energy comes with it, pushing everything apart even faster. It is a runaway effect. It's crucial to understand that these two hidden actors, dark matter and dark energy, are completely different things. Even though they both share the name dark, they are locked in a cosmic battle for the fate of the universe. Dark matter pulls. It tries to hold structures like galaxies together. Dark energy pushes. It acts on the vast empty spaces between galaxies, forcing them further and further apart. On a local scale, like within our own galaxy cluster, dark matter's gravity wins. The Milky Way and the Andromeda galaxy are actually being pulled together by gravity and are on a collision course. But on the grandest scale of the entire cosmos, dark energy is the clear winner. It is pushing distant galaxy clusters away from us at an accelerating rate. We can think of the universe as a grand theatre. For all of human history, we have been watching the performance focusing on the single brightly lit actor on the stage at the 5% of visible matter. We studied this actor's every move, thinking it was the entire play, but we have now realised that the entire show is actually being controlled by two other actors moving stunted in the darkness. One actor, dark matter 27%, is the stagehand in the shadows building, the stage holding the scenery together and guiding the visible actor's movements. The other actor, darker energy 68%, is not just an actor, but a force that is actively pushing the very walls of the theatre apart, moving the stage and the audience away from each other at an ever-increasing speed. We, the audience, can only see the effects of these hidden actors on the one performer we can see. We have just opened our eyes to the 95% of reality that truly directs the play. The story of dark matter begins not with a new discovery, but with a deep puzzle. It started in the 1930s with a brilliant and famously eccentric astronomer named Fritz Zwicky. He was studying a massive city of galaxies called the Coma Cluster, a dense collection of hundreds of galaxies all bound together by their mutual gravity. Zwicky decided to weigh the cluster. He knew he couldn't put it on a scale, so he used two different methods. First, he measured all the light coming from the galaxies. He counted the stars he could see, estimated their mass, and added it all up. This gave him the visible mass of the cluster. Second, he used a clever trick of physics. He measured how fast the individual galaxies inside the cluster were moving. He saw them zipping around like angry bees in a hive. He knew that for the cluster to hold together, there had to be an enormous amount of gravity pulling everything inward. If there wasn't enough gravity, these fast-moving galaxies would simply escape and fly off into deep space, and the cluster would dissolve. When Zwicky did the math, his two answers didn't match. In fact, they weren't even close. The speed of the galaxies told him there was a massive amount of gravity at play, but the light from the stars told him there was only a tiny amount of matter. It was a shocking contradiction. The cluster was moving so fast it should have torn itself apart long ago. The amount of stuff he could see was not nearly enough to generate the gravity needed to hold it all together. Zwicky calculated that there must be hundreds of times more stuff in the cluster than what was visible. He called this missing invisible substance Dunkel Materia, or dark matter. It was a substance that had gravity, but it did not shine, reflect light, or interact with light in any way. For decades, most of the scientific world ignored Zwicky's discovery. His measurements were difficult to make, and the idea of a universe filled with the invisible stuff seemed too strange. The puzzle was filed away as a curious anomaly. The mystery was reopened and finally taken seriously in the 1970s, thanks to the pioneering work of an astronomer named Vera Rubin. She wasn't looking at distant clusters, she was studying individual spiral galaxies, much like our own Milky Way. She wanted to measure how fast stars were spinning around the center of a galaxy. Think about our own solar system. Mercury, which is close to the Sun, orbits very quickly. Earth farther out moves slower. Neptune and Pluto at the edges crawl along. This makes perfect sense. Almost all the mass and therefore the gravity of our solar system is concentrated in the Sun at the center. The farther you get from the Sun, the weaker its gravitational pull becomes, and the slower the planet's orbit. Everyone assumed galaxies would work the same way. All the bright stars, gas and dust are packed into the glowing center. Therefore, stars near the center should move quickly, while stars at the far dim edges of the galaxy should be moving very slowly. Vera Rubin and her colleague Kent Ford built extremely sensitive instruments to measure these speeds. They pointed their telescopes at the Andromeda Galaxy and measured the speeds of stars at many different distances from the center. What they found was one of the most profound and shocking discoveries in the history of astronomy. The stars near the center were moving fast just as expected, but the stars at the outer edges were not slowing down. They were moving just as fast as the stars in the middle. The galaxy was spinning like a solid disk, not like a solar system. This galaxy rotation curve at a graph of speed versus distance was flat. It should have been a steep downward slope. This discovery was terrifying from a physics standpoint. Imagine swinging a rock on a string. To keep it in orbit, you have to hold the string tightly. The faster the rock spins, the harder the string pulls. If the string breaks, the rock flies off. The stars at the edge of the galaxy were like that rock. They were moving so fast that the gravity from all the visible stars, gas and dust was not nearly enough to hold them in orbit. The string of gravity should have broken. The galaxy should be actively tearing itself apart, flinging its outer stars into the blackness of intergalactic space. But it wasn't. The galaxies were still. They were whole. Vera Rubin realized there was only one possible conclusion. The visible galaxy of stars was just the tip of the iceberg. It had to be embedded in a much larger, completely invisible spherical halo of other matter. This halo must contain most of the galaxy's mass stretching far beyond the visible light. Its immense gravity was the string holding those fast-moving outer stars in their orbits. This was the same invisible stuff Zwicky had found 40 years earlier. This time the evidence was undeniable. Galaxy after galaxy showed the same flat rotation curve. Dark matter was real and it was everywhere. These discoveries forced scientists to change their entire view of the universe. Dark matter is not just some strange exotic idea. It is the most essential ingredient of the cosmos. It is the glue that holds the universe together. When Vera Rubin's data became clear, it showed that the matter we know, the stuff that makes up stars, planets, and people called baryonic matter, is just a small fraction of what's out there. For every 1 pound of normal matter, there are about 5 pounds of dark matter. We are the leftovers. The universe is dominated by a substance we cannot see and do not understand. Without dark matter, galaxies as we know them could not exist. Our own Milky Way would have disintegrated billions of years ago. The stars, including our sun, would have spun off into the void. The importance of dark matter becomes even clearer when we try to build a universe from scratch. Scientists use powerful supercomputers to create simulations of the cosmos. They start with a digital Big Bang and program in all the laws of physics we know, like gravity and the expansion of space. First, they try to run the simulation using only normal matter, the hydrogen and helium gas created in the Big Bang. The result is a failure. In the simulation, gravity tries to pull the gas together, but the universe is expanding and the gas is hot and pushes back. The simulation cannot form large structures. It produces a few small clumpy galaxies, but the result looks nothing like the universe we observe. Then they run the simulation again. This time they add the magic ingredient dark matter. They program the computer to include 5 times more dark matter than normal matter. The result is a stunning success. Because dark matter doesn't interact with light or radiation, it isn't pushed around like normal gas. It only feels gravity. Very early in the universe's history, this dark matter began to collapse under its own weight. It formed a vast, invisible, 3-dimensional network of massive filaments, nodes, and halos, stretching across the entire universe. Astronomers call this the cosmic web. This invisible web is the skeleton of the cosmos. Dark matter is the scaffolding upon which our visible universe is built. The process of forming a galaxy did not start with stars, it started with dark matter. Think of building a house. You must first build a foundation and a frame. You cannot just throw bricks and wood into a pile and hope a house appears. In the early universe, dark matter was the foundation and the frame. It collapsed first, creating massive invisible clouds called halos. These halos are gravity wells, deep pits in the fabric of space and time. Only after these dark matter halos were in place did the normal matter, the gas, begin to fall into them like water swirling down a drain. The dark matter's gravity pulled the gas in from all directions. As the gas fell to the center of the invisible halo, it was compressed, it started to spin, and it flattened into a disk. Inside this spinning disk of gas, the material became dense enough to ignite, giving birth to the first stars. What we see as a galaxy, the beautiful spiral of stars and glowing gas, is just the normal matter that has pulled in the very center of a much larger, much more massive and completely invisible dark matter halo. When you look at a photograph of the Andromeda Galaxy, you are only seeing the glitter. The real structure, the scaffolding that holds it all together, is a sphere of dark matter thousands of times larger and more massive than the bright part you can see. This means that we are living inside one of these clouds right now. Our planet, our sun, and our entire Milky Way galaxy are all hurtling through space embedded deep inside a giant invisible halo of dark matter. This substance is streaming through the room you're in, passing through your body and the Earth itself as if you were not even there. It is the silent, unseen foundation of our cosmic home. To understand the strangest and most mysterious part of our universe, we first have to go back to the beginning of modern cosmology, back to Albert Einstein. After he published his groundbreaking theory of general relativity, which explained how gravity works as a curvature of space and time, he applied it to the entire universe. But his own math gave him a result he did not like. His equations showed that the universe must be dynamic. It had to be either expanding or contracting. It could not simply exist as a static, unchanging stage. In the early 20th century, this was a philosophical problem. The prevailing scientific view was that the universe was eternal, infinite, and most importantly stable. It just was. To fix his equations and make them match the obvious fact of a static universe, Einstein added a new term. He called it the cosmological constant. It was a tiny invisible pressure a sort of anti-gravity that would push space apart just enough to perfectly balance the inward pull of gravity. It was a mathematical adjustment, a fudge factor, to keep the cosmos standing still. Then in the 1920s, an astronomer named Edwin Hubble changed our view of reality. Using the massive Hooker telescope at Mount Wilson, he observed distant nebulae and made two profound discoveries. First, these nebulae were not clouds of gas in our own galaxy, they were entire other galaxies' island universes, just like our Milky Way millions of light years away. Second, and more importantly, he measured the light from these galaxies and found it was stretched. The light was shifted toward the red end of the spectrum, a phenomenon called redshift. This is the same effect that causes a police siren to sound lower in pitch as it moves away from you. This redshift meant that almost every galaxy was moving away from us. Hubble's observation proved that the universe was not static, it was expanding. The farther a galaxy was, the faster it was moving away, implying a single explosive origin point, what we now call the Big Bang. When Einstein heard of this, he supposedly remarked that his cosmological constant, the fudge factor, he invented to keep the universe still, was his biggest blunder. He had missed the chance to predict the expanding universe from his own theory. For the next 70 years, the story of the universe was a simple one. The Big Bang started the expansion like an explosion throwing shrapnel outward. But all the matter in the universe, the galaxies, the stars, the gas and the mysterious dark matter, was pulling everything back together with its gravity. The great question for astronomers was, what is the ultimate fate of the universe? Think of throwing a ball straight up into the air. Gravity is constantly pulling it down, slowing its ascent. If you throw it slowly, it will stop and fall back down. If you throw it very, very fast, escape velocity, it will slow down, but it will never quite stop escaping Earth's gravity forever. Cosmologists believe the universe was the same. The expansion was the throw, and the combined gravity of all matter was the pull slowing it down. The entire scientific community was trying to measure how much the expansion was slowing. Would the universe slow down and eventually collapse in a big crunch, or would it slow down but coast forever? In the 1990s, two rival teams of astronomers set out to measure this deceleration. To do this, they needed to look at things that were incredibly far away. Because the speed of light is finite, looking far away is also looking back in time. They needed a standard candle, an object that always has the same actual brightness no matter where it is in the universe. If you know how bright something actually is, you can tell exactly how far away it is by measuring how dim it appears. A 100-watt light bulb looks much dimmer from a kilometre away than it does from a metre away. Their perfect standard candle was a Type 1a supernova. This is a special, rare and incredibly violent event. It happens in a binary star system where a small dead star called a white dwarf orbits a larger companion. The white dwarf's intense gravity siphons gas from its partner. It eats, until it reaches a precise critical mass about 1.4 times the mass of our Sun. At this exact point, it can no longer support itself, and it ignites in a catastrophic thermonuclear explosion. Because they all explode at the same mass, they all reach the same peak brightness. Both teams, the Supernova Cosmology Project and the HISIS Supernova Search Team, used the world's best telescopes to hunt for these exploding stars in the most distant galaxies they could find. They were looking for supernovae that exploded billions of years ago. They would measure the supernova's redshift, telling them how much the universe has expanded since it exploded, and its brightness telling them how far away it was. They fully expected to find that the very distant supernovae were brighter than they should be. Why? Because if the universe's expansion was slowing down, it meant that in the past it was expanding faster. This means the supernova would be closer to us and thus brighter than a constantly expanding model would predict. The results when they came in '98 were a profound shock. They were one of the most stunning discoveries in the history of science. The distant supernovae were not brighter. They were dimmer than expected. They were dimmer, which meant they were farther away than all the models predicted. How could they be farther away? There was only one possible mind-bending conclusion. In the time since those stars exploded, the expansion of the universe had not slowed down. It had sped up. This was unbelievable. It was like throwing a ball in the air and watching it suddenly shoot upward faster and faster, defying gravity. Something was pushing the universe apart. Something was acting as an anti-gravity, overwhelming the combined pull of all the matter and dark matter in the cosmos. Scientists were forced to name this mysterious repulsive force dark energy. Suddenly, Einstein's biggest blunder did not look like a blunder at all. His cosmological constant occurrence, the anti-gravity pressure he added to his equations, was the perfect mathematical description for this new accelerating force. He had put it in his equations to create a static universe, but it seems he may have been right for the wrong reason. This dark energy, this pressure built into the very fabric of empty space appears to be real. It is not just a mathematical trick. It is the dominant force in the cosmos, making up nearly 70% of the total energy of the universe. We do not know what it is, where it comes from, or why it has the exact strength it does, but its discovery has opened a new vast and dark horizon, and it defines the ultimate accelerating and very lonely-looking future of our universe. While the ancient light from the cosmic microwave background and the bending of space-time give us a picture of the entire universe, we can also find powerful evidence right in our own cosmic neighbourhood. The story of this discovery begins with a persistent astronomer named Vera Rubin in the 1970s. She was studying something that seemed very simple: how fast stars orbit the centre of their own galaxies. Think about our own solar system. Mercury, which is closest to the Sun, moves incredibly fast. Earth moves at a medium speed. Pluto, way out at the edge, moves very, very slowly. This makes perfect sense. The Sun's gravity is strongest near the centre, and gets much weaker the farther out you go. Less gravity means a slower orbit. Everyone assumed galaxies would work the same way. The stars at the bright dense centre should be moving quickly. The stars on the outer edge, far from the visible stuff, should be moving very slowly. Vera Rubin made the measurements, and what she found was shocking. The stars at the edge of the galaxy were moving just as fast as the stars near the centre. This is like finding that Pluto orbits the Sun at the same speed as Mercury. It completely breaks the laws of gravity unless there is a massive amount of invisible stuff we can't see. Her calculations showed that for the galaxy to hold itself together at these speeds, it must be surrounded by a massive invisible halo of material. This halo's gravity would be grabbing onto those outer stars, keeping them in their high-speed orbits and preventing them from flying off into deep space. This stuff had to be completely dark. It didn't shine, it didn't block light, and it wasn't made of stars, gas, or dust. It was something else. This observation, now called the galaxy rotation curve, was one of the first and most solid pieces of evidence for dark matter. The case of the cosmic giants. Around the same time, other astronomers were looking not just at single galaxies, but at massive clusters of galaxies. These are the biggest structures in the universe, held together by gravity, containing hundreds or even thousands of galaxies, all swirling around each other. An astronomer named Fritz Zwicky had actually noticed a problem here way back in the 1930s. When he measured the speeds of the galaxies in the Coma cluster, he found they were moving at incredible velocities, like a swarm of angry bees. They were moving so fast that the combined gravity of all the visible galaxies in the cluster wasn't nearly enough to hold them together. The cluster should have flown apart millions of years ago, with its galaxies scattering in all directions. Zwicky proposed that there must be a huge amount of Dunkel materia, or dark matter, filling the space between the galaxies. The gravity from this invisible mass was the glue holding the entire cluster together. For decades, his idea was largely ignored. But with modern telescopes, we found a second clue in these same clusters. When we look at them with X-ray telescopes, we don't see the galaxies, but we see a gigantic cloud of superheated gas hotter than the core of the Sun. This gas fills the entire cluster. Again, physics gives us a problem. A gas that hot should have evaporated, boiling off into space millions of years ago, just like steam from a pot of water. Why is it still there? The only way that gas can be held in place is if it's trapped by an overwhelmingly powerful gravitational field. When astronomers calculated how much gravity was needed, they got the same answer Zwicky did. The visible galaxies and the hot gas only make up a tiny fraction of the total mass. The rest, about 85% of the total matter, is completely dark. The scaffolding of the universe. The evidence from the cosmic microwave background, CMB, and gravitational lensing tells us what the universe is made of. The evidence from galaxy rotation and clusters tells us where that dark matter is. But there's a third line of evidence that tells us why it is essential, the large-scale structure of the universe. When we map the locations of millions of galaxies, we find they aren't scattered randomly. They form a breathtaking pattern, a vast cosmic web of long filaments and dense nodes, all surrounding giant empty regions called voids. The question is, how did the universe build this web? We have run powerful computer simulations to try and grow a universe from scratch. We start with a smooth soup of matter and energy, just like the CMB showed us, and let gravity pull things together over 13 billion years. If we run the simulation using only normal matter, the 5% we know about it fails. Gravity is too weak and normal matter gets pushed around by light and radiation. It's too slow and inefficient. You can't form the complex web we see today, but if we run the simulation again this time, adding the 27% of dark matter, everything clicks into place. Because dark matter doesn't interact with light, it isn't pushed around. It started clumping together immediately after the Big Bang pulled together by its own gravity. It formed a massive invisible scaffolding for the universe. The normal matter, the gas and dust, then felt the powerful gravity of this dark framework and was pulled into it like iron filings aligning to a hidden magnet. The galaxies and clusters we see today are just the lights on this vast invisible structure. The cosmic web is in reality a dark matter web. Without it, none of us would be here. The runaway expansion. All this evidence paints a clear picture of dark matter, the 27% of the universe that acts as its gravitational skeleton. But this leaves us with the biggest piece of the pie, the 68% known as dark energy. The evidence for this is perhaps the strangest of all. For most of the 20th century, astronomers had one big question. Will the universe expand forever, or will it collapse? Everyone assumed the expansion which started with the Big Bang must be slowing down. Gravity from all that normal and dark matter is constantly pulling everything back together. It was just a question of how much it was slowing. In the 1990s, two teams of astronomers set out to measure this slowdown. To do this, they needed standard candles, objects of a known consistent brightness. They used a special kind of exploding star, a Type 1a supernova. These explosions always happen in the exact same way and reach the exact same peak brightness. Because we know exactly how bright they are, we can use them as perfect distance markers. A 100-watt light bulb looks dim from a kilometre away and bright from a metre away. By measuring the dimness of a Type 1a supernova, we can calculate precisely how far away it is and how fast it's moving away from us. The teams found dozens of these supernovae in very distant galaxies, and they all discovered the same impossible thing. The distant supernovae were dimmer than they were supposed to be. This wasn't an error. It meant the supernovae were farther away than all our models predicted. For them to be that far away, the universe hadn't been slowing down. Sometime in the last few billion years, the expansion of the universe started to speed up. This was a discovery that won the Nobel Prize. The universe is not just expanding, it's accelerating. What could cause this gravity-only pulls? To make the universe accelerate, you need a force that pushes. You need a form of anti-gravity. This mysterious repulsive force, which seems to be a property of space itself, is what we call dark energy. It is pushing the galaxies apart, and it is the single most dominant force in the cosmos today. We have arrived at the strangest part of our journey. We have proven using the spinning of galaxies and the bending of starlight that 85% of all matter in the cosmos is missing. We call it dark matter because it does not interact with light. But the dark part is an understatement. This stuff is utterly invisible. It is completely transparent. The paradox of dark matter is that it is simultaneously the most dominant substance in the universe and the most elusive. Based on our calculations, billions of dark matter particles are streaming through your body, through the Earth, and through the empty space between planets every single second. They are all around us like an invisible ocean we are submerged in. Yet we feel nothing. They do not bounce off our atoms. They do not warm us up. They do not cast a shadow. They pass through solid rock as if it were empty space. This is because they mostly ignore the fundamental forces that build our world. They ignore the electromagnetic force which gives us light, touch, and chemistry, and the strong nuclear force which holds our atoms together. This presents a terrifying challenge for scientists. How do you catch a ghost? How do you detect a particle whose entire identity is based on not being detected? The answer is to build the quietest, most sensitive traps ever created and to wait for a miracle. Underground experiments, why we dig deep. The surface of the Earth is a terrible place to look for dark matter. It is not noisy in the way a city is, but in a cosmic sense. Our planet is constantly being bombarded by high-energy particles from space called cosmic rays. They come from the sun and from exploding stars billions of light years away. If you built a sensitive dark matter detector in a lab on the surface, it would be overwhelmed. Thousands of cosmic ray particles would smash into it every second, creating thousands of false positives. It would be like trying to hear a single pin drop in the middle of a rock concert. To find the silence they need, scientists must go deep underground. They use old deep mines, gold mines in South Dakota, nickel mines in Canada, or road tunnels bored deep under mountains in Italy or China. They build their experiments a mile or more beneath the surface. This massive shield of rock, thousands of feet of solid stone, absorbs almost all the cosmic rays. Down in these deep dark labs, scientists build their traps. The most famous experiments such as LZ Lux Zeppelin, Xenon 1T now, Xenon NT, and Pandax particle and astroparticle xenon are all based on the same idea. They build a large clean tank and fill it with an incredibly pure liquid, usually the noble gas xenon. This xenon is kept very cold and is surrounded by some of the most sensitive light detector sensors ever made. The whole setup is a trap waiting to be sprung. The scientists just wait. They are waiting for a single dark matter particle having flown through the galaxy and through a mile of rock to finally collide just once with the center, the nucleus of a single xenon atom. It's like a game of cosmic billiards. If the dark matter cue ball hits the xenon billiard ball, the xenon atom will be knocked loose. When this happens, the recoiling xenon atom creates two signals, a tiny immediate flash of light and a second slightly later signal as it releases a few electrons. The sensitive cameras lining the tank are designed to see this specific 1-2 ping. This is why they need the silence. These experiments are so sensitive that they must be shielded not just from cosmic rays, but even from the natural low-level radiation in the rock walls of the mine itself. They are trying to hear a single ghostly whisper in a room of absolute silence. Candidate 1 WIMPs. Weakly interacting massive particles. For decades, the most popular and promising candidate for dark matter was the WIMP. The name tells you everything. Weakly interacting. It doesn't interact with light, but it does feel the weak nuclear force. This is the force responsible for some types of radioactive decay. It is incredibly weak and only works over extremely short distances, which is why WIMPs can pass through planets. But weak is not zero. It means a collision can happen. It's just incredibly rare, which is what the xenon experiments are bad it gone. Massive particle. WIMP is a heavy particle. Not heavy like a bowling ball, but heavy on a subatomic scale, perhaps 10 to 1,000 times heavier than a proton. The WIMP miracle. The reason physicists loved the WIMP idea so much was because of something called the WIMP miracle. It was a stunning coincidence. Scientists asked a simple question. If a WIMP-like particle, heavy and weakly interacting, was created in the super-hot environment of the Big Bang, how many would be left over today? In the early universe, particles were constantly being created and destroyed. As the universe expanded and cooled, there was no longer enough energy to create new WIMPs. The existing WIMPs could only be destroyed by colliding with each other. But as the universe kept expanding, they drifted further and further apart until they could no longer find each other. Their numbers froze in place. When physicists did the math, the leftover amount of these theoretical WIMPs perfectly matched the exact amount of dark matter we actually measure in the universe today. It was a beautiful, simple explanation. A leading theory known as supersymmetry or SUSY even predicted the existence of such particles. The silence from detectors and the Large Hadron Collider LHC. There is just one problem. The WIMP miracle was so good that it made specific predictions. It predicted how heavy WIMPs should be and how often they should ping those xenon detectors. Based on these predictions, the big experiments like LZ and Xenon should have found them by now, but they have found nothing. The silence is deafening. There was a second way to find WIMPs. We could try to make them. This is the job of the Large Hadron Collider LHC, the giant particle accelerator in Switzerland. The LHC smashes protons together at enormous speeds to create new heavy particles. If WIMPs exist, the LHC should be able to create a pair of them. Because they are dark, they would fly out of the detector without being seen. But scientists could detect them by looking for missing energy, a collision where the energy going in does not equal the energy coming out. The LHC has been smashing particles for years. It has looked for this missing energy signal, and just like the underground mines, it has found nothing. This double failure has put the WIMP idea in serious trouble. Physicists are now being forced to think again. Candidate 2 axions. With the WIMP fading as the top candidate, many scientists have turned their attention to a very different, very strange and very light particle, the axion. While WIMPs are heavy, axions are almost impossibly light, billions or even trillions of times lighter than an electron. They are so light that they don't really behave like individual particles. Instead, they behave like a giant invisible wave sloshing through the universe. Like the WIMP, the axion wasn't invented for dark matter. It was proposed in the 1970s to solve a completely different puzzle in physics called the strong CP problem. It was a theoretical fix for a math problem. Years later, physicists realized that if this particle existed, it would have been produced in enormous quantities in the Big Bang and would be a perfect dark matter candidate. Because the axion is a wave, You detect it in a different way. You don't wait for a ping. Instead, you try to tune in to its frequency like a radio. The theory predicts that if an axion passes through a very strong magnetic field, it has a tiny chance of converting into a photon, a particle of light. This is exactly what experiments like ADMX Axion Dark Matter experiment are doing. ADMX is essentially a very cold, hollow metal chamber, sitting inside one of the most powerful magnets on Earth. This chamber is a resonator. Scientists slowly tune the chamber, like turning the dial on a radio sweeping through different frequencies. If they hit the exact frequency that matches the axion's mass, the axion wave will resonate inside the chamber and convert into a tiny signal of microwave light. It would be like hearing a single faint pure note broadcast from the dark matter ocean. So far, ADMX has heard only static, but the search continues. Other ideas. Self-interacting. Dark matter and primordial black holes. PBHs, the silence from the WIMP hunts has caused an explosion of creativity. If dark matter isn't a simple WIMP or a simple axion, what else could it be? Self-interacting dark matter, SIDM. This idea proposes that dark matter is ghostly to us, but not to itself. What if dark matter particles can bounce off each other, creating a kind of internal pressure? This idea is popular because it seems to solve some puzzles about how dark matter is shaped in the centers of small galaxies. Primordial black holes PBHs. This is the most radical idea. What if dark matter isn't a new particle at all? Should it if it's just a huge swarm of ancient black holes? These would not be black holes formed from dead stars, but primordial ones, formed in the chaotic first second of the Big Bang. They could be as small as an asteroid or as large as a planet. They would be massive, invisible, and have gravity a perfect dark matter candidate. The most profound mystery in all of science began with a simple observation: distant exploding stars appeared dimmer than they were supposed to be. In 1998, astronomers were using these exploding stars called supernovae as cosmic mile markers to measure how much the universe's expansion was slowing down. They assumed gravity, the force that pulls everything together, was acting as a brake on the expansion that started with the Big Bang. What they found was the exact opposite. The explosions were dimmer because they were farther away than expected. This meant the expansion of the universe was not slowing down, it was speeding up. This discovery was so shocking it was like throwing a ball into the air and watching it shoot into space instead of falling back to Earth. Some unknown force is pushing the universe apart, overpowering the pull of gravity on the largest scales. Scientists gave this mysterious force a name: dark energy. It is the dark component of the universe, making up nearly 70% of everything that exists, yet we have almost no idea what it is. The quest to identify it has led to several strange and fascinating possibilities. The ghost in the machine, an energy of empty space. The simplest explanation is also the strangest. It comes from an old idea by Albert Einstein, which he later called his biggest blunder. When Einstein first developed his theory of gravity, general relativity, his equations showed the universe should either be expanding or collapsing. But in his day, everyone believed the universe was static and eternal. To fix his equations and make the universe hold still, he added a new term, the cosmological constant. It was a mathematical fudge factor, representing an energy that was an inherent property of space itself, pushing outward to perfectly balance gravity's pull. A few years later, astronomers discovered the universe was expanding and Einstein threw his idea in the trash. But now it's back. Perhaps Einstein was right about the constant but wrong about its size. What if this energy of empty space is real? This idea gets even stronger when we look at the bizarre world of quantum mechanics. According to quantum theory, a vacuum-pure empty space is not empty at all. It is a bubbling, chaotic foam of virtual particles that pop into existence and disappear again in timescales too short to measure. Think of it like the surface of a pot of water that is simmering but not quite boiling. Even though it looks calm from a distance upwards, tiny bubbles are constantly forming and vanishing. This fizz of particles gives empty space an energy. This is called vacuum energy. According to Einstein's equations, this vacuum energy would have a remarkable property: it would have negative pressure. This is just a physics term for a push. It's a perfect candidate for dark energy. As the universe expands, new space is created. And because this energy is a property of space itself, this new space also has energy. This creates a self-perpetuating cycle. More space leads to more dark energy, which leads to more space faster and faster. This theory fits our observations of the universe almost perfectly. There's just one problem. In fact, it's been called the worst prediction in the history of physics. When physicists try to calculate how much vacuum energy there should be based on quantum theory, the number they get is breathtakingly large. The predicted energy is 1 followed by 120 zeros, a number so large it's hard to even write times stronger than the gentle acceleration we actually observe. If the vacuum energy were truly that strong, the universe would have been ripped to shreds. Fractions of a second after the Big Bang, stars and galaxies would have never been able to form. The fact that we are here means the real value is tiny. This is a crisis. Our two best theories of the universe: general relativity for the very large and quantum mechanics for the very small, give us completely opposite answers. It's possible that some unknown process cancels out almost all of this energy, leaving just the tiny bit we see. But why we don't know, it leaves us in a difficult position. The cosmological constant is the simplest idea and fits the data best, but we have no idea why it has the value it does. The shapeshifter, a new field in the cosmos. This leads to the second major candidate. What if dark energy is not a constant property of space? What if it's a new thing, an invisible universe, spanning energy field much like a magnetic field? Scientists call this idea quintessence, named after the mythical fifth element that ancient Greeks believed filled the heavens. Unlike the cosmological constant, this field would not be constant. It would be dynamic, meaning it could change over time and vary from place to place. In the early universe, this quintessence field might have been very weak, allowing gravity to do its job of pulling matter together to form stars and galaxies. But as the universe expanded and all the matter, both regular and dark matter, thinned out, this new field would have stayed, and its repulsive push would have become the most powerful force in the cosmos. This neatly explains why the acceleration only started recently in cosmic terms about 5 billion years ago. This idea is exciting because it opens up a whole range of possibilities for the future of the universe. The fate of everything depends on how this field decides to change. The big freeze. If the field stays at its current strength or weakens slightly, the universe will simply keep expanding faster and faster. Galaxies will fly away from each other until they are so far apart they disappear from view. The stars will eventually burn out and the universe will become a cold, dark and empty void. This is currently the most accepted scenario. The Big Rip. But what if the field gets stronger over time? This is a terrifying idea known as phantom energy. The push would grow so powerful that it would eventually overcome all other forces. First, it would rip our Milky Way galaxy apart. Then it would overcome the gravity holding our solar system together, sending Earth flying into the dark. As the push intensified, it would become strong enough to overcome the chemical bonds holding planets and even our bodies together. Finally, in the last moments of time, it would become strong enough to tear apart the very fabric of atoms. The universe would be torn to pieces. The Big Crunch. A third possibility is that the field could one day reverse itself. The push could turn into a pull, causing the universe's expansion to slow down, stop, and then reverse, sending all of space hurtling back toward a single point in a fiery Big Crunch, perhaps setting the stage for a new Big Bang. While quintessence solves the problem of a static energy, it introduces a brand new puzzle which scientists call the coincidence problem. The measurements show that right now, in the long 13.8 billion year history of the universe, the density of all matter which pulls and the density of dark energy which pushes are relatively close to each other. Matter makes up about 30% and dark energy makes up about 70%. But this is a fleeting moment. In the past, matter was completely dominant. In the future, dark energy will be. Why are we, the human race, just happening to evolve at the exact special moment in cosmic history when these two completely different forces are in a coincidental balance? If dark energy is a dynamic field, it makes this coincidence seem even less likely. It requires the field to have a very specific value at a very specific time. This specialness makes many physicists uncomfortable, as science prefers laws that are universal, not ones that depend on us living at a lucky moment. The ultimate twist: what if it's not energy at all? There is a third, more radical possibility. Both of the previous ideas assume one thing: that Einstein's theory of gravity is correct on all scales. We've tested general relativity in our solar system and by observing black holes, and it passes every test perfectly. But what if it's incomplete? What if on the truly vast scales of the entire universe, gravity just works differently? This idea is called modified gravity. Perhaps Einstein's equations are just a very good approximation, just as Isaac Newton's laws of gravity were a brilliant approximation that worked perfectly for centuries until Einstein came along. We are now seeing a behavior cosmic acceleration that Einstein's theory can't explain without adding a dark component. Maybe the problem isn't a new energy, maybe the problem is the equation. In these theories, there is no dark energy, there is no vacuum energy, no quintessence field. The acceleration we see is simply a feature of gravity itself. On the small scale of a solar system or a galaxy, gravity pulls. But on the cosmic scale of billions of light years, gravity's behavior changes and it begins to push. This is a very difficult idea to prove. It's hard to change Einstein's theory, which is famously elegant and successful, without breaking all the things it gets right. But it remains an active area of research. If this idea is correct, it would be the second great revolution in our understanding of gravity. We are left at a crossroads. The universe is accelerating and we are forced to choose between three uncomfortable solutions. An energy of empty space that our best theories predict should be 20 orders of magnitude stronger than it is. A new changing energy field that just happens to be the right strength at the exact moment we are here to observe it. The possibility that our most successful theory of gravity, general relativity, is wrong. Whatever the answer turns out to be, it will fundamentally change our picture of the universe, our origins, and our ultimate fate. We've spent decades trying to find dark matter and dark energy. We've built our standard model of the universe, lambda CDM, on the assumption that these two invisible components exist and make up 95% of everything. But we haven't found a single particle of dark matter. We have no idea what dark energy is. This persistent failure leads to a scary but thrilling alternative. What if the problem isn't the stuff in the universe, but the rules that govern it? What if the missing energy and missing gravity aren't missing at all, but are just signs that our fundamental theory of gravity? Albert Einstein's general relativity is incomplete. It wouldn't be the first time this has happened. For centuries, Isaac Newton's law of gravity worked perfectly. It could predict the fall of an apple and the orbit of the moon. But in the early 20th century, astronomers noticed it wasn't quite right. It couldn't explain the strange orbit of the planet Mercury. Einstein's general relativity fixed this, showing that Newton's law was just an excellent approximation that breaks down at high speeds or in very strong gravity. The question today is Einstein's theory also just an approximation? Does it break down on the enormous scales of galaxies and the entire universe, or in the regions of incredibly weak gravity? This idea is broadly known as modified gravity. MOND, the original challenger. The first serious attempt to challenge the status quo came in the 1980s, long before dark energy was even discovered. An Israeli physicist named Mordechai Milgrom was focused on the galaxy rotation problem, the fact that stars on the edges of galaxies orbit far too fast. Instead of inventing an invisible halo of dark matter to provide extra gravity, Milgrom proposed a simple tweak to Newton's laws. He called it MOND, which stands for Modified Newtonian Dynamics. The idea is surprisingly simple. MOND suggests that Newton's law of gravity is correct only when the gravitational pull, the acceleration, is strong, like it is here in our solar system. However, when the acceleration becomes incredibly unbelievably weak, as it is for a star on the extreme outer edge of a galaxy, the rule changes. In this very low acceleration zone, MOND says that gravity doesn't fade away as quickly as Newton predicted. It remains slightly stronger over long distances. This stronger long-range gravity is just enough to grip those outer stars and keep them in their fast orbits. No dark matter is required. The amazing thing about MOND is how well it works. For most individual galaxies, you can just look at the visible matter, the stars, and gas apply the MOND rule, and it correctly predicts the galaxy's rotation speed. It's a stunningly accurate prediction from a simple rule, whereas the dark matter model has to be adjusted for each individual galaxy. However, MOND is not a perfect solution. It failed in clusters. While MOND were good for individual galaxies, it failed when applied to massive clusters of galaxies. Even with MOND's modified gravity, the galaxies within these clusters were moving too fast. To explain this, MOND still needed some form of dark matter, though perhaps less of it. It couldn't explain the CMB. MOND has an extremely difficult time explaining the patterns of hot and cold spots in the cosmic microwave background, the afterglow of the Big Bang. The standard dark matter model, on the other hand, predicts this pattern with breathtaking precision. It wasn't Einsteinian. MOND was a modification of Newton's gravity, not Einstein's. This meant it couldn't make predictions about the expansion of the universe or the bending of light gravitational lensing, modifying Einstein. Because simple MOND had its limits, scientists realized that to truly challenge the standard model, they had to modify the king of gravity theories, Einstein's general relativity. This is vastly more difficult. General relativity is a complex and beautiful set of equations that describe gravity as the curvature of space-time itself. Changing it without breaking all the things it gets right, like the orbits of planets, the existence of black holes, and the bending of light, is like trying to change the foundation of a skyscraper without having it fall over. This led to a jungle of complex theories. We don't need to know the deep mathematics, just the general ideas. Far gravity. This is pronounced F of R gravity. In Einstein's theory, the curvature of spacetime is described by a mathematical term R, the Ricci scalar. The equations are clean and simple. In FR theories, scientists replace this simple R with a much more complicated mathematical function, FR. By designing this function in a specific way, they can make gravity behave exactly like Einstein's in high gravity zones like our solar system, but behave differently on cosmic scales. The goal is to create a function that naturally mimics dark energy, causing the universe's expansion to speed up all by itself without needing any mysterious energy field. TeV's tensor vector scalar gravity. This was one of the most famous attempts to create a relativistic version of MOND. It was a very complicated theory that introduced new fields into the fabric of spacetime to make gravity behave like MOND on galaxy scales, but like Einstein on solar system scales. These theories are mathematically dense, but they all share one goal: to create a single unified theory of gravity that can explain everything from Mercury's orbit to galaxy rotation to the accelerated expansion of the universe without needing to invent dark matter or dark energy. The reality check: how to test a new gravity. For decades, these modified gravity theories were just fascinating ideas on a blackboard. It was hard to find a test that could clearly prove one right and the other wrong. That has now changed. We have two powerful new ways to put these theories on trial. One, the growth of cosmic structure. How do you tell the difference between a universe filled with dark energy and a universe run by a different law of gravity? You watch how things grow. Think of it this way. In the standard model, gravity from matter and dark matter pulls things together to build galaxy clusters, while dark energy pushes space apart, slowing down that building process. There is a specific growth rate predicted by this cosmic tug-of-war. Many modified gravity theories, however, predict that gravity itself is stronger on large scales. This would speed up the formation of cosmic structures, making the universe clumpier than Einstein's theory would allow. We can now measure this. New projects like the Euclid satellite and the Vera C. Rubin Observatory are mapping billions of galaxies across billions of light years. By comparing the clumpiness of the universe in the ancient past far away to the clumpiness nearby today, they will create a definitive history of cosmic growth. This data will show once and for all if structures grew at the rate Einstein predicted, or at a different rate as modified gravity suggests. 2. The sound of a gravitational wave. While the growth of structure is a slow test, a sudden and violent event in 2017 provided a killer blow that wiped out a huge number of modified gravity theories almost instantly. On August 17, 2017, observatories on Earth detected gravitational waves, ripples in spacetime itself, from two neutron stars crashing into each other. The event was named GW 170817, but that's not all they saw. Just 1.7 seconds after the gravitational waves arrived, space telescopes detected a burst of light, a gamma-ray burst from the exact same point in the sky. This was the crucial measurement. The collision happened 30 million light-years away. This means that over a journey of 30 million years, the light waves and the gravitational waves raced each other across the cosmos and arrived at Earth at virtually the exact same time. This proved beyond any doubt that gravitational waves travel at the speed of light. This simple fact was a death sentence for many modified gravity theories. A key prediction of many of these complex theories, including TeVis and many FR models, was that gravity would interact with the new fields they proposed. A side effect of this was that gravitational waves should travel slower than light. GW 170817 acted as a swift and brutal executioner. It proved these theories wrong. They simply could not be the correct description of our universe. This one event was a massive thundering victory for Albert Einstein. It showed his 100-year-old theory of general relativity was correct yet again in a way he could have never dreamed of testing. While some modified gravity theories survived this test, the options have been drastically narrowed. The puzzle of dark matter and dark energy remains, but Einstein's framework for now stands stronger than ever. We find ourselves after a long journey of discovery standing at the shore of an immense cosmic ocean, with 95% of its waters remaining utterly dark and unknown. Everything we have ever seen, every star, every galaxy, every planet, and every person is built from a mere 5% of the total ingredients of the universe. The rest, a vast majority of reality, is composed of dark matter and dark energy shadow entities. we can only detect by the subtle gravitational pull they exert on the little bits of light we can see. This profound realization forces us to confront the most fundamental questions of our existence. It is not just a gap in our knowledge, it is a chasm. And standing at the edge of this chasm, we must ask, what is our place in all this darkness? This leads us to the most unsettling puzzle in all of physics, the anthropic principle. The problem is that the laws of our universe, the fundamental constants that govern reality, appear to be astonishingly precisely fine-tuned for life to exist. The strength of gravity, the mass of an electron, the energy density of space itself, these values are set with a precision that defies belief. If you were to change any of these numbers by even a hair's breadth, the universe would have been sterile. Stars would not have formed, or they would have burned out too quickly for planets to cool. The chemistry required for life, the simple fact of stable atoms, would have been impossible. The universe appears to be balanced on a knife edge perfectly calibrated to allow for complexity, consciousness, and us. Why? This question pushes us toward two staggering and completely different answers. The first is that the universe was in some way designed for us, that this fine-tuning is not an accident but a feature, a sign that the existence of conscious observers was somehow the goal from the very beginning. This idea makes many scientists uncomfortable as it feels more like philosophy or theology than testable science. The second answer is perhaps even more bizarre: the multiverse. This theory proposes a statistical escape from the fine-tuning problem. It suggests that our universe is not the only one. Instead, there may be an infinite cosmic foam, a sea of other universes, each branching off with its own random set of physical laws. In the vast majority of these universes, the laws are wrong, they are dead empty and sterile. Gravity might be a repulsive force, atoms might instantly fly apart. But if you create an infinite number of universes, statistics guarantee that by pure chance some of them will have the lucky combination of laws that allows for stars, planets, and life. We simply find ourselves in one of these lucky universes because we could not exist in any of the others to observe them. We didn't win a lottery that was fixed for us, we just live in the one timeline where our lottery ticket happened to be a winner out of an infinite pile of losing tickets. But as we debate these grand, untestable theories, we must also consider a more humble and perhaps more troubling possibility. What if we are simply wrong? What if dark energy and dark matter are not real substances at all, but just placeholder concepts for a deeper ignorance? This is where the analogy of the ether serves as a powerful warning. In the 19th century, scientists were certain that light which travels in waves must need a medium to travel through, just as sound waves need air and ocean waves need water. They called this hypothetical invisible substance the luminiferous ether. They believed it filled every corner of space. Scientists spent decades designing brilliant experiments to detect this ether, to measure our motion through it. Every single experiment failed. Then Albert Einstein proposed his theory of special relativity. He argued that the ether was not just hard to find, it was completely unnecessary. The speed of light, he showed, was a fundamental constant of the universe itself. Light did not need a medium. In an instant, the ether, a central concept of physics, vanished, exposed as a collective fiction, a placeholder for an incorrect understanding of reality. Is dark energy our modern ether? Is it just a fudge factor we invented to make our equations match our observations of an accelerating universe? It is entirely possible that 100 years from now, a new Einstein will provide a new theory of gravity, a new understanding of space and time that perfectly explains cosmic acceleration without needing any dark energy at all. It is possible that 95% of the universe is not a thing but a profound misunderstanding of the rules. This brings us to the most honest and important truth of all we do not know. The fact that 95% of reality remains a complete mystery is not a failure. It is the greatest invitation in the history of human thought. It is the ultimate expression of cosmic humility. To look at the entirety of our knowledge, our art, our science, our philosophy, and to admit that it is all built on just 5% of the picture is the first and most crucial step toward understanding the rest. This vast, dark ignorance is not a wall, it is a door. It is a promise that the greatest discoveries are yet to come. It is a guarantee that the human adventure of exploration is far from over. This mystery is a gift, an engine for curiosity that will fuel generations of thinkers, dreamers, and explorers yet to be born. And so we end where we began, a tiny flicker of light in an overwhelming darkness. We, the 5% of luminous matter, are the anomaly. We are the stuff that, against all odds, organized itself into complex patterns, into life, into consciousness. Perhaps this is our role. We are the universe's way of becoming aware of itself. Think of it this way. The other 95%, the silent dark majority, may form the immense body of the cosmos, setting its structure and driving its future. But we, the luminous 5%, are its mind. We are the part of the universe that can look back at the whole. We are star stuff that has evolved to the point of being able to build telescopes to study the stars from which we came. We are the cosmos made conscious, the universe's eyes and ears, turning our attention back toward the immense silent darkness that birthed us. We are the universe's attempt to understand its own totality. We, the light, are the part of reality that gets to be astonished by the dark. This is our place. We are the conscious edge of the 5% staring into the 95% and asking, "What are you?" And in doing so, we ask the most profound question of all, "What then am I?"